Hello, everyone. My name is Aleksei. I'll be chairing a session where we have, of policy learning, Olivier will start to tell us about multi-objective recommendation via multivariate policy learning. And please ask your questions on Slido. There's plenty of questions you probably have. Go ahead and write them down.
All right, thank you. Hello, everyone. So when we're talking about, when we're talking about the sort of general problem of doing a recommendation, we typically have a user, we have a certain item, something like a video, and then users have a way to get some sort of user item, sort of interactions, right? And very often we talk about clicks, but this can be likes, this can be anything, but we tend to focus on optimizing a single objective. But users can do many things. They can maybe click on these items, they can view them, they can skip videos, they can share them. There's a whole swath of really sort of different types of engagements and different types of objectives that we might want to sort of optimize for. And so one way this is done very often in practice is through scalarization. And so what that means is essentially the score that you're going to give to a certain user item pair is just going to be a function of all of those different things. So you have a model that's going to tell you something about how likely is the user to click this, how likely is the user to like this, how likely is the user to view this until the end. And then the final score that you'll use is just going to be a weighted average of those things. And so these weights, what these weights should be, that's the core focus of this talk. And we try to solve that doing sort of policy learning. So when you're doing policy learning, you're essentially just learning a function. So we have a function, it has a certain set of parameters xi, is going to take in a user, and the output of that function is going to be a new set of parameters. And these are going to be used to define a certain distribution. And then when we're actually going to serve this to users, we're going to sample. So we have a user, we're going to look at, well, what is the sort of Gaussian distribution here that I get? I'm going to sample weights, and I'm going to serve these weights to the user and see what happens. And the core focus here is going to be on learning this function. So we somehow want to learn the parameters xi star are the optimal ones, and we want to get these parameters that are going to maximize the expectation of reward we get. Reward can be essentially anything, but we're going to look at long-term user retention, for example, the real things that we sort of care about. And we want to maximize the expectation of that random variable, given that we sample the weights according to the distribution we get under these parameters. Now, how do you get an estimate of the expectation of reward? That's typically using a sort of counterfactual estimator. But I would say the whole approach we have is kind of more or less sort of agnostic to that. So it doesn't really matter what you're going to use, but you plug in your favorite estimator. And when you do that, you might get something like this. You might be able to plot the values of your parameter xi on the x-axis, an estimate of the expectation of the reward on the y-axis, and then we can very simply just say, okay, we're doing some sort of gradient descent on this, and we're finding the optimal parameters. But we typically don't really look at the expectation because there might be high uncertainty, and the uncertainty might behave in weird ways. So we want to get a certain confidence interval around the expected reward that we're going to get, maybe something like this, and then we want to optimize a lower bound on this. So we're going to be slightly pessimistic because these things work very well, it turns out, in practice. And so you would want to get this point in the space of parameters that's going to maximize the lower confidence bound. And so that all sounds great, but it does mean you need some way to compute a reliable sort of confidence interval. And that's also not that hard, it seems. So we can, through the CLT, the sort of central limit theorem, you're able to actually just do this by getting an estimate for the mean, an estimate for the variance. There should be a square root on there, by the way. It should be the standard deviation. A little typo in the slide. But using this, you're actually able to get a decent confidence interval. And it's guaranteed by the central limit theorem that you're going to get the right coverage in the limit of infinite samples. And I typically don't work with data sets like that. So what you get in practice looks like this. You have the sample size on the x-axis, you have your sort of coverage on the y-axis, and it is going to converge at 95%. We know that for certain. But we're not really sure when that's going to happen, and in practice, it really might not happen very quickly. And so the problem is that we're typically going to be in the sort of upper left here, actually, where the samples we get per context and per action are actually not that many, and we might actually be underestimating the variance, and we don't really get the right coverage. And so we're trying to be pessimistic, but maybe we're not being so pessimistic enough. And so one way to maybe try and measure when this is happening is using something called the effective sample size. And that's essentially a metric that's going to tell you how informative your sample is. So you might have 1 million samples, but you're trying to get an estimate on a target policy, and you're trying to estimate, well, if I would be able to get samples from my target policy directly, how much information would I get from them? And how much information do I have in my sample if I want to translate it to that quantity? That might sound very vague, and I'm really sort of leaving out all of the math details on the slide here, but just to like sort of build some intuition, if you have two like so distributions that are really far apart and there's not a lot of overlap, you might have a low effective sample size. When they are much closer together, there's a lot of overlap, you might have a high effective sample size. And so essentially what we are really trying to propose here is that, well, when you have a high effective sample size, probably that's the best you can do. You should just rely on the central limit theorem to get your CIs, and they might be great. But when you have a low effective sample size, you might be in a situation where you really are sort of underestimating the variance, and we're going to inflate the width of the confidence intervals that you get. And so it turns out that that works really well. So this is a plot from the paper. Again, lots of details about the setup that I won't share. But essentially, we're looking at different sort of target policies. On the x-axis, you have the sample size. On the y-axis, you have the sort of coverage you get for your CIs. And then there's different lines that show essentially different ways to estimate the effective sample size. So the blue line for n is just the sample size, and then there's a few different ones. And we can see, of course, when the sample size increases, they all tend to converge at 95%, which is exactly what you want. But in lower sample regimes, it turns out that using this method to inflate your variance is actually going to work pretty well. And so a different way to look at this plot is to look at, well, how many samples do we need before we actually get a confidence interval that gets the advertised level? And it turns out we can get pretty big improvements here. So when you just would say, okay, the sample size we need, when we're just using the CIs by the CLT, that's going to be the baseline. How many fewer samples do we need if we're using this correction? And it turns out that that can go up to 60 times fewer samples, which I would say is really quite a lot. Okay, great. But now I'm certain there will be a few people in the room who are thinking, well, this is a recommender systems conference. All of this is basically pure statistics. Why are we here? So does this actually lead to getting better recommendations when you're using policy learning on this other lower bound that is going to have better coverage? And so first of all, we can do an offline experiment. So we're going to try to learn this function for the weights. We're going to really sort of keep it simple. We'll just learn the mean, and we'll treat the variance of the policy as a hyperparameter. And we're going to target retention. And we can do an off-policy evaluation of this, and that might look like this, right? So for different values of the variance in the learned policy on the x-axis, we can look at an estimate using the SNPs estimator for the relative increase in reward you get on the y-axis. And so when there's lots and lots of variance in the policy, essentially everything smooths out, and you're not really able to improve things a lot because everything, all those policies will be similar. If you have lower and lower values of sigma, that means you're essentially learning a very, very narrow distribution, very peaked, and you will have very high variance because of a very low effective sample size. And so this looks great, really, because if you look at the y-axis, where we might get up to a 300% increase in users that are using the platform, which looks great. These numbers are right, probably. You have a confidence interval that has some guarantees, but they're not very useful, right? Because that is never going to happen in practice. So, it seems to work, but it's not very useful because of the variance. And so maybe instead of looking at targeting retention as a reward, we can look at a learned reward function that is going to be a good proxy for retention. And there's a lot more detail on how we do this in a recent paper we had at sort of KDD. And there's a lot more detail in the paper as well. But essentially, we can use certain proxies that are vetted, and we know that they actually have a high correlation with retention, but they're much more sensitive and much, much easier to move. So here again, we have the same thing on the x-axis, the same thing on the y-axis. But the scale is a lot nicer, it looks a lot more realistic. And now you can see that there are certain values of sigma there where the sort of confidence interval does not include 1. So we have a significant result in our offline test, and this looks very promising. So when we have that, we want to do an online test, and that's exactly what we did. So these are results from an A/B test on the Moch platform, which is essentially a short video app with a single feed. So we just learn for all of the users, they all get their weights, and then we measure what's happening. So we have this learned reward function, which is exactly the thing we're trying to move. It does move, so we have the same result as we got from the offline test, so that's pretty nice. And there's a few more metrics that are also moving in the right direction, which is pretty nice. It turns out here we're not really able to move retention in a short-term A/B test, though. We also did a second A/B test on the ShareChat platform, which has multiple different feeds, and we optimize different weights for different kinds of feeds. And there it turns out we were actually able to, first of all, still move the learned reward, so still the offline results match the online results, which is always pretty nice. But then here we're also able to have significant improvements on the time users are spending on the platform, and there's more users who are coming back to use the platform the next day. There's far more in the paper. I think it's a quite dense paper, and I thought it was a bad idea to have 17 slides with long equations. But if that's the stuff you would like to hear more about, I would really suggest you read the paper. And I'm also happy to answer any questions you might have. Thank you.
Thank you, Olivier. We have a few questions on Slido. Do we have a question from the audience here? No? Let's go with the Slido ones, if I can unlock my phone. So, first, did you try using confidence sequences instead of intervals with finite sample guarantees to guarantee coverage?
What was the first word there? Did I try using confidence?
Sequences instead of intervals.
I do not know what that is, but I would be very interested to learn about it. So if the person could reach out to me, I would like to learn more.
Okay. Whoever wrote it, talk to Olivier later. The second question is, how is your approach different from distributional reinforcement learning?
Different from distributional reinforcement learning?
Yeah.
I would say there's, it's not very different. I mean, these are methods that live in the same realm. We're not doing reinforcement learning, being, there's no state. We don't try to optimize multiple actions in a sequence where it's just a single action. But yeah, I think they're using similar ideas on how to get some robustness guarantees.
Okay.
Okay.
Thank you.
Thank you.
Any other questions? No? All right. Thank you, Olivier.